Howdy, and welcome to my video on exponent laws. Um, I will be going over some practice problems on the Virtual Math Learning Center. The link to the problems I am using today will be in the description. By doing these practice problems, I hope I will demonstrate to you all exponent laws and how to simplify exponents and radicals. Okay, so let's start off with question 1. It's asking us to simplify, and they give us a reminder, right, that when you simplify, you should try to minimize the appearance of each variable. And in this case, the hint is each variable should only appear at most once, and every exponent should be positive. Okay, so we'll write out the question. 12 times xy negative 1 cubed, and then x negative 2 y squared, all that squared, over, negative here, 20 x negative 4 negative 2 xy negative cubed squared. So I like to work horizontally and then vertically. What I mean by that is that I will simplify the numerator and the denominator and then simplify the whole thing. So let's just start with that. So at the top, first thing I can do is distribute the 3, like these exponents, outer exponents, right? And it's 2 into the inner exponents. And once I do that, I get the following. So negative 12. Actually, I'm going to simplify the constants, okay? So we get 3 instead. And then we get x to the third. Switch colors. Y to the negative 3. And remember, when we're distributing like this, we are multiplying the exponents together. Then x to the negative 4. And y to the positive 4. For our denominator, we get 5 instead, where we divide by 4. And for our x, it becomes x to the 8th, negative 4 times negative 2. Next term, it's x squared, right? 1 times 2. And, oh my god, 2, there you go. And then y to the negative 6, negative 3 times 2. Okay. Now from here, I can combine my like terms, so my x's and my y's. So my x's here and my y here will just be the same. So from here, negative 3, and on top I'll have x. 3 minus 4 is negative 1. My y's have negative 3 plus 4, which is positive 1. All of this over 5 times x to the 10th, right? And then my y to the negative 6. I can now rewrite this as one line, so negative 3/5. And then what I want to do is take these and move them over, and I have to use a negative exponent law, right? Because I'm going from denominator to numerator, so I have to flip the sign on the exponent. So my x negative 1 is the same, the y to the 1 is the same, but I now have x to the negative 10 and y to the positive 6. That's the wrong color. There we go. And now we can combine like terms. So you have x negative 1 times plus negative 10, sorry. We get negative 11. And then for our y's, 1 plus 6 is 7. One last step is that I need to deal with this negative exponent. So negative 3 y to the 7, right? Then 5 on bottom, and x to the 11th. That is my answer. For number 2, we're going to simplify the radical expression. So, we can work horizontally here, but since I have the same root, what I'm going to do is actually undistribute this cube root and then simplify the fraction I have and then go from there. So when I take out the 1/3, right, the cube root, so it's an exponent of 1/3, I have negative 24 x to the 4th y squared z to the 6 over 81xy to the 1/3 power, right? Now if we look at the inside here, so we have the negative 24 x to the 4 y squared z6 over 81xy. This is, we have negative 24, 81. And we want to move these up to the numerator. So I have to remember to flip the signs as they switch sides of the fraction. So x negative 1, y negative 1. The fraction, negative 24 over 81. Let's do negative 8 over 27. So dividing both top and bottom by 3. Or multiplying top and bottom by 1/3, if you will. We can combine our like terms together. We get x cubed 4 minus 1. We get y to the 1st 2 minus 1. And then we should still have z to the 6. Okay. When we rewrite this, this is negative 8. I'll keep it negative 8. X cubed y to the 1st z to 6. This negative doesn't really matter where it goes with. I just put on top because I know I can. Over 27. Okay. And now we need to put it back into the 1/3. Bring it here and bring back the 1/3 root. And we're going to redistribute. So we will now have a cube root of negative 8x cubed y z to the 6 over the cube root of 27. The top becomes negative 2, right? We have 3 x's and we need groups of 3, so we can take 1 out. We don't have enough space for y, but there are 6 z's and we need groups of 3. So we have 2 groups of these z's we can make. And what's left is the cube root of y over 3. And there you go. That is our answer. For the next problem, we're all adding and subtracting. So we just need to simplify each of these terms. So root x cubed is root x squared times root x. And the reason I wrote out this 2 is because notice my root is even and my exponent inside is even. But when I get the x out, it has this implied 1, right? Which is odd. When you have this even, odd pattern, right? Even exponent in the inside, even root, and your resulting exponent is odd, you need the absolute value to make sure that it does not accidentally cause any issues. Okay. Then we have our root x. The square root 4x cubed is almost the same. So it's square root 4 times square root x cubed. We know from square root 4 is 2, right? And square root of x cubed, we can see from above, is absolute value x, root x. And root x is obviously just itself. I can't do more with that. Rewriting the equation yields me absolute value x times root x plus 2 absolute value x root x minus root x. That's really it. That's all you can really do. If you were to factor this out, right, you can group out the root x, the common factor, and get root absolute value x plus 2 absolute value x minus 1, and combine these together, right? The same term, so you can combine these. Root x 3 absolute value x minus 1. This is your factored form. Okay. Now, number 4, which you rationalize the denominator. It means no radicals underneath. We only want whole exponents. So the easiest way is to use difference of squares. Note that difference of squares goes like this, okay? Or recall rather. We have a minus sign already, right? So we just need to multiply by the same term with the flipped sign. And you call it the conjugate. So if it's a minus sign, flip to a plus sign. If it's a plus sign, flip to a minus sign. I'm going to rewrite the question here, or the expression here. Now conjugate, right, is we just flip the sign. It's a plus sign now. But now on top, I need to multiply by the same thing to make sure that I am multiplying essentially by 1, right? Because a fraction that's the same on top and bottom is equal to 1. And when you multiply by 1, the value doesn't change. Even in this case, it would just look different. When we multiply, the bottom follows difference of squares. So you get 3 root 6 squared minus 4 root 3 squared. And then we have to distribute the entire top. So 4 root 6 times 3 root 6 is 12 times 6, right? Because the square roots cancel when we multiply them. And the number is the same, right? Then you have 4 root 6 times 4 root 3. That is 16 root 18. 3 root 3 times 3 root 6 is 9 root 18. And 3 root 3 and 4 root 3 gives us 12 times root 3. And again, root 3 times root 3, it's root 3 squared. It takes away the square root. And it gives you, oh, I didn't write 3. It gives you just the 3, okay? We can continue simplifying this. So we get 72, right? Plus 25 root 18 plus 36 over, so it is 3 times, not 3 times, 9 times 6, right? 3 squared is 9, root 6 squared is 6, minus 16 times 3, 4 squared is 16, root 3 squared is 3. Keep simplifying. 108 plus 25. That root 18, right, is 3 root 2. Because root 18 equals root 9 times 2, which is root 9 times root 2, which is 3 root 2. Okay? Over 54 minus 48. And we get 108 plus 75 root 2 is over 6. That is your final answer. If you wish, you could split a fraction into 2 like this, using adding fractions law, whatever. You get 18, I believe, plus divide by 3 top and bottom, 25 root 2 over 2. Okay. So let me rest my hand real quick. Oof, long one. Okay, so now same thing here, right? We're rationalizing the denominator. You see this minus sign, and we have these square roots, right? I mean, just if one exists on either side, right? Like root x minus y, you'd still use the conjugate. So x minus y over root x minus root y. Okay. So if I multiply by conjugate in the bottom, right? That's root x plus root y. Again, I need to do the same thing on top to make sure that I am multiplying by a fraction that is equal to 1. So that, again, I am not changing the value, just the way it looks. Using difference of squares, the bottom becomes root x squared minus root y squared. However, the top, I'm going to leave it as a product of two terms. Okay. I could FOIL, but I'd rather keep stuff unfoiled until I absolutely need to. Okay. I simplify the bottom. So root x squared is just x, and root y squared is just y. We can see that we can cancel these two terms, and we're left with root x plus root y. Okay. That's my answer for number 5. And number 6, we're going to solve for this fraction first. Okay. So a to the 5/4 times a negative 3/8 over a negative 3/4. Now we're going to use exponent laws, and we're going to bring this to the numerator. So we need to not forget to flip the sign. So a 5/4, a negative 3/8, and a positive 3/4. You know that using exponent laws, right? When you multiply all these together, you get 1a as the base, and you add all the exponents together. 5/4 minus 3/8 plus 3/4. This gives you, using 8 as a common denominator, 10 over 8 minus 3 over 8 plus 6 over 8, which is 7 over 8 plus 6 over 8, which is 13 over 8. So my final exponent is 13 over 8, at least for the inside, right? We can substitute this back in, and we get a 13 to the 13/8, right? To the power of 2/3. And when we distribute, right, to the one term, we're just multiplying, right? You raise a power to a power, you just multiply. Well, not power to a power, but if you have a term raised to a power, all in parentheses raised to another power, you just multiply. So this equals a to the power of 13/8 times 2/3, which gives you a to the 26 over 24. And you can simplify that to 13 over 12. Okay. It's an exponent, so this is my final answer. And with that, this concludes my video on exponents.